Dagmar. And so, yes, it's a pleasure and it's especially an honor to introduce Dagmar Sternad, my co-organizer for this workshop, outstanding researcher in human motor control. And so, I came to know Dagmar first by reading one of her publications, and that made my day, because I felt like it solved two major problems in robotics. One is that she showed that sensory motor noise could be overcome by humans by learning new simple strategies. And I thought, well, now we don't have to look for robots that are ultra precise. We just need to find good strategies to overcome this noise, and that's good news. And apparently human can do that in very few trials, even 15 trials, which seems incredibly fast. And then the second thing was to say, humans also overcome these things because they are capable to learn the redundancy that there is in the task, the multiple different solutions. That again, it clicked. In robotics, we tend to always want to have the optimum. But in fact, what matters most from an optimal control viewpoint is often feasibility. In a way, that's what Dagmar was underlying there, is that humans are not caring so much necessarily for optimality, but more for feasibility. With this, I'll give you the floor. And I cannot see your screen yet.
No, because
Nope.
I'm doing it right now. So let me do this. So thank you very much, Odd, for the very kind introduction. And what you mentioned is probably also the core of what I'm trying to convey in my talk today about learning and control in skilled interactions with objects. And underlying this, I want to show also an approach that I have developed over the years, which I think has been helpful for me and us to uncover some of these ideas, how humans can learn. So I'm obviously a human person, unlike the robotic people, and I just want to pay tribute to the amazing feats that robotics researchers have done, in particular in manipulation. But then I want to remind you that we still have to learn, as this, one of my favorite examples, shows what humans actually can do. And I think you agree with me that the versatility that this gymnast and others show is still unsurpassed. She manipulates objects of all sorts, flexible ones like the ribbon, by manually rigid objects with her wrist and fingers, but not only that, she can manipulate objects with all parts of her body. So how did she do this? How did she learn this? What kind of control principles did she learn? So when you look into the literature and people talk about motor learning, they typically say, well, motor learning is about becoming more accurate and less variable, sometimes faster, but definitely less variable. Whereas I would like to hold that humans are always variable. They cannot get rid of it because there is variability and random noise. So what I would like to propose with my idea on motor learning is that learning is finding solutions that make noise and small errors matter less. And the concepts that speak to this idea are stability and variability. So a quick intro to learning. So this is a typical schematic of what learning is all about. And that is, you begin with some non-zero error, a novel task. And with practice, you decrease that error to a certain degree, to a certain level. And with a bit of luck, this learned task has long-term stability, retention, such that we can say acquisition is an increase, a delta in skill. But this is too simple because, as I emphasize noise and variability, we need to differentiate the learning process by definitely paying tribute to the initial phase where variability plays an enormous role, exploration. This is followed by a fine tuning where this noise is attenuated, but not only attenuated, but maybe channeled into non-relevant dimensions. And then retention is again keeping that skill for a while, for a long while, and keeping it stable. Now, I will in this talk also show you what we can do in order to enhance and accelerate this learning by a variety of interventions. So here we have again the non-zero error at the beginning, and an intervention aims to accelerate and enhance learning such that there is an extra delta in skill, so that you get even better. So as I mentioned, we have developed an approach that I think has helped us to make quantitative points. So to begin, we pick a task that has interesting features to us, and of course that needs to be justified. And then we mathematically model this task and then analyze the task to derive a space of solutions that then allows us also to virtually render the model task so that we have full control over the task and can make model-based manipulations. And as we make it interactive, virtual interactive task, we can analyze how humans perform the task. Then, based on our insights, we can design interventions to enhance and accelerate learning. And lastly, our hope is to also uncover some principles that are of interest to the robotics community, as well as for human-machine interactions. So let me again take inspiration from the marvelous manipulation abilities of gymnasts, but then do an embarrassingly simple simplification and reduce the manipulation by giving our humans eventually a racket in the hand. So we are making our problem simpler by eliminating the hand and reducing the contact to a rigid paddle with instantaneous contact when we ask our subjects to bounce a ball on a racket, just like this little boy here. So reducing a rhythmic interaction task to this very simple element, we begin by mathematically modeling the task. And here again is the paddle and the ball. This is confined to the vertical dimension, instantaneous impact and ballistic flight of the ball. There is no effect of the ball on the racket. Then, as simple as it is, we can do stability analysis, in this case, local linear stability analysis, to identify what are the criteria that makes this rhythmic interaction stable, dynamically stable. And you see on the left, on the here, you see two simulations where the racket trajectory is this sinusoidal pattern and the ball ballistic flight interacts with the paddle at a particular phase and acceleration. As the stability analysis has identified, we can obtain stable solution as exemplified by the lower trace, that where perturbations applied at one contact converge to the stable solution if the acceleration of the racket is below zero, lower bounded by the parameters of the model, coefficient of restitution, and the gravitational constant. So how do we then examine subjects and how they perform this task in a virtual environment? Here, our subjects hold a real paddle that has a rigid rod attached, and we measure the vertical displacements. We also measure directly the accelerations, and then our subject sees this extremely simple rendering of the task, and with the online shown racket movement, is asked to bounce the ball to hit this target line rhythmically. So how do we get from the model to the data? Here are human data, and by looking at the acceleration measured directly, we extract the acceleration just prior to the contact. And then in trials with about 60 bounces. We take the average acceleration as well as the average height error, that is the difference between the peak of the ball and the target height. And then we look over, in this case, over 48 trials, and we can see what is expected, namely that the error goes down with practice. And looking at the racket acceleration at impact, we can see that after about 13 trials, which is about 20 minutes, they only then choose a solution where the acceleration is negative. We have identified this region as stable versus this is unstable. So this tells us two things: that humans find these non-intuitive smart solutions with stability that are insensitive to noise and can preempt error corrections. Mind you, they don't have to do this. As we can see at the beginning, they can control errors by feedback control, but they choose to find this dynamically stable solution. Based on this finding, we then ask the question, how can we actually help subjects to find such a solution faster? Now, here is just a segment of this racket sinusoidal trajectory, where we again indicate that after maximum velocity, which is in the middle of this sinusoidal schematic trajectory, is in the racket impacts, ball racket impacts should be in this upwardly decelerating part of the trajectory. What we did was we slightly manipulated the ball racket contact such that we actually used for the simulation a contact that is 50 milliseconds earlier. So with this, we conveyed to subjects completely implicitly that they should move their contact higher up into this veridically negative acceleration area. So did they achieve what we wanted them to achieve? Two groups, a control group. Again, the height error declines with practice, and here, as well as our time shift group decreases their error. And importantly, in this gray area, we withdrew that manipulation and both groups bounced the ball with veridical display. The acceleration, our critical variable, shows a more rapid decline into the negatively accelerating area. And importantly, subjects retain that performance. So, an interim summary on this. I wanted to show you how learning about the acquisition phase of this simple task, where we identified stability to be a core feature, we designed an intervention that indeed accelerated and improved their bouncing skills with some at least 3 days lasting power. So we learned that human subjects improve performance and exploit the stability of the task. This implicit guidance, human subjects had no idea what was happening, is going beyond error feedback, where we just show explicitly the error, but we somewhat tweak their interactions that then changes their performance in ways that was actually retained. So this part emphasized stability. Let me move on to another task where I emphasize variability and its role. So going from our gymnast and do an embarrassingly vast step to simplify the task, we look at a throwing task, throwing a ball attached to a pendulous string, and the ball has to be thrown around a center pole. And this is Skittles, this is a pub game, and pub games often inspire scientists. We follow our same task dynamic approach. This is our task. How do we go from the task to the model? We go yet one more simplification step further, in that we show our task from a top-down projection such that we can simplify the dynamics of the throwing to one where the ball in white here is at a rest position suspended by two orthogonal springs, and the rest position is exactly at that center post. If the subject then deflects the ball, as shown here, and releases the ball with a given tangential velocity, then the ball traverses an elliptic path that is meant to go through a target skittle here. And if there is no hitting, we calculate the error by the minimum distance between the trajectory and the target at any moment in time. So to exemplify a core feature of this excessively simple task, that is redundancy. So everybody knows the trajectory is determined by two variables, the position and velocity at release. And the success is defined by one variable, the distance error to the target. So we have a 2-to-1 redundancy. And here this graphics shows how two ball trajectories, number 2 in green and 3 in red, both end up at the same target hit, while the blue dashed line is a different throw that has a non-zero error.
2 minutes left, Dagmar. 2 minutes left.
Yeah.
2 or 3 minutes left. Yeah.
We summarize, we summarize the performance possibilities here in that execution space, where the two hitting trajectories in green and red lie on this parabolic manifold, the set of zero error solutions, and these are the non-zero error solutions as the blue trajectory. So I show the virtual setup here. Our subject has their arm on a manipulandum, grasps a ball, and by lifting the finger from a force sensor, they can throw the ball, as shown here, to hit a target. So looking at the evolution of individual throws, each point here is one release. We can see how subjects explore that solution space and gradually converge towards the manifold. We have separated 3 conceptually different ways how subjects can find that manifold. That is by translation, rotation, and by noise reduction. And this is what we see in stages when subjects practice this skill. But there is yet another way of attaining stability. And this is shown here by taking that same execution space as state space, where we show full arm trajectories. An early one, as the blue one, which only has 2 intersections with a manifold, and the green one, a later one, which has an entire timing window. We then quantify the timing error, that is the temporal distance from the ideal release point, and the timing window, that is the length of time we can travel along the manifold. And of course we claim, or we expect, that this timing window will give us stability or tolerance to errors and noise. We tested this in 2 different target locations with 2 different solution manifolds. And indeed, we show that while error declines and success rate goes up, we can see that the timing error declines and the timing window that we achieve by shaping the trajectory increases in both manifolds. So the pattern is invariant. We shape our trajectories, we reduce the timing error, although timing error saturates because of our limited timing resolution. So I want to just skip these slides briefly and conclude that I wanted to show you 2 examples, what I see as learning, that is strategies to make noise matter less by gaining insights into the acquisition process by a detailed analysis of the task and then look into human choices. We got some insights that we then took to design interventions. In ball bouncing, stability was the core principle. We showed that noise tolerant strategies can be attained by dynamic stability, and we can lead to implicit guidance interventions. And variability in skittles, again, is a dominant feature where we showed that noise tolerant strategies are obtained via co-varying the trajectory with the manifold. I did not show you how we can actually enhance this, but you can obviously ask me. And we have another task that Salah already presented, where we now transport a ball, and this is meant to be just a brief plug for 2 talks later on in the conference, Salah Bazi and Rashida Nayem. And with this plug, I want to thank my lab, my funding sources, and everybody listening to me. Thank you.